Okay, let's continue our discussion of the magnetic field. So yesterday we looked at a problem. We had magnetic field oriented into the plane of the board or paper. I'm used to thinking about chalkboards. And we fired a positively charged particle into that magnetic field. And so we took a positively charged particle, we shot it into this magnetic field such that V is perpendicular to the magnetic field. We discovered that the resulting trajectory was circular. So this is a circular trajectory. It had radius r, and experimentally it was determined that the velocity had a magnitude which was unchanged, and so it exited with the same velocity that it entered with, so that the magnitude of the velocity is constant. We know that the direction is changing. And so that implies an acceleration. And that acceleration is radial in nature. And that implies that there must be a net force. We did some experiments to come to the conclusion that the force is equal to QVB sine of theta. We're going to call that the magnetic force, and we described each of these terms in order. But now, if we look at a last experiment, right? So again, we're gonna take our magnetic field oriented into the plane of the paper. And this time, however, instead of firing a positively charged particle into the field, we're going to shoot a negatively charged particle. So again, this is magnetic field into plane of the paper, same as up here. This time, as I said, we're going to take a negatively charged entity. We're going to shoot it into the magnetic field, and we're going to set up this experiment so that B and V are identical to the scenario above, and what we experimentally observe is that the charged entity now, instead of being on a circular trajectory as it appears up here, right? It now is rotating, so to speak, in the opposite direction. So it's actually moving in this direction. This one was moving in this direction, counterclockwise. This one's going to be going around in a clockwise direction. Everything else about those two experiments is the same. The velocity magnitude with which it exits is identical The radius is identical. Everything about these two situations is the same except for the sense of rotation, so to speak. So how do we explain these? It certainly is not explained using the force law that we arrived at, that I just circled. We need a new piece of information here to describe whether the force in the upper case here, right, as this charged particle enters this field, the magnetic force, like the acceleration, is always going to be directed toward the center of the circle. Okay, so there's the direction of the acceleration and the direction of the force. In this particular case, the force as it enters the field is going to be in opposite direction. If we take a look at this, as opposed to this, everything is the same except for the direction of the force. The magnitude would be identical because Q is identical except for the sign. V is identical, B is identical, so the magnitudes of each of these is the same, right? So this doesn't at all explain the direction of the magnetic force on that charged particle. So we need a way of describing that, and so we conjure up what is called a right-hand rule. It's a right-hand rule because you need your right hand to use it. And so, again, you could probably pull up some YouTube videos, and I'll look for something that's really good and put it into the email. But the way this goes is you would place the fingers of your right hand. Okay, so place the fingers of your right hand along the direction of the velocity vector. You curl your fingertips into the direction of the magnetic field. And your thumb points into the direction of the instantaneous magnetic force. It takes some practice, but but I think that you could get it rather quickly. And again, I will show you this when we Zoom tomorrow morning, and I will also send you guys a good YouTube video that's short and to the point. So so right-hand rule. We have now the magnitude. We have now the magnitude of the magnetic force, and we know how to get its direction. We get its direction from the right-hand rule, right? So this gives the direction of the magnetic force. Beautiful. Okay. Now we're in a position to do all kinds of fun things. All right. So so for instance, right? Let's go back and play the same game. This time with a little twist, right? So we have a magnetic field which is oriented into the plane of the page. and we'll assume that it's going to be a positively charged particle that we're gonna throw in there. Okay, let me just get one more row here. There we go. Now there's nothing magical about magnetic field into. We could have very easily had magnetic field out of, and so again, it's a lot easier to draw X's than it is to draw circles with little dots in it, believe it or not. So magnetic field into. We're going to take a positively charged entity, and we're going to shoot it into this magnetic field, again where V is oriented perpendicularly to B. Doesn't always need to be perpendicular to B, right? It could be at oblique angles, and we'll talk about that a little bit perhaps, but for now, let's leave V perpendicular to B. And the instant that I shoot this object into that magnetic field, I'm going to instantaneously turn on a magnetic field in this part of space. Okay, so I'm going to shoot that charged entity in, and at the same instant I'm going to turn on a magnetic field in the left-hand portion here. Okay, and what will result now, instead of just getting this semicircular path that we got before, what we're going to do is we're going to establish a circular path, and there again the velocity, the velocity vector is always going to be tangential to the direction of motion. The magnitude of that velocity is going to be constant. Okay, and so there's going to be a magnetic force as it enters the field. So there's the magnetic force, right? Magnetic force always directed toward the center of the circle. Magnetic force always directed toward the center of that circular trajectory, which is going to be of some radius r. Okay. Now, as I said before, this is a problem in uniform circular motion. Uniform circular motion. And we can then look at Newton's second law, which says that F net is going to be equal to mass times acceleration. The net force is equal to the object's mass. Right? This charged entity will also have associated with it some mass. The only real player here is the magnetic force. Again, we're looking at small charged particles, and by doing so, the gravitational force is very, very small, very, very small, and can be neglected. And so the only force then is going to be the magnetic force, and that's going to be in magnitude equal to Q VB sine of theta. That's going to be equal to the object's mass times its acceleration, but the acceleration is radial or centripetal in nature. Theta is 90 degrees, since V is perpendicular to B. And so then we have QVB times the sine of 90 degrees is equal to m times the radial acceleration, which you will recall is v squared over r in this case. This gives us then QVB is equal to m v squared over r. And that's great just the way it is, but let's recall from circular motion, from circular kinematics, that v, the tangential speed, is equal to r omega. In this particular case, then v is equal to the radius of the circular motion times omega. And so we can actually now just plug that into here, and we get now that QB, right, because we can cancel, whoops, we can cancel one of these with one of these. And so then we have then that QB is equal to mv over r. QB is equal to m r times omega over r. The r's cancel, and we get omega is equal to QB over m. And you will recall that omega is an angular frequency. Okay, actually that's really it's got a special name in this context, right? So omega is called the cyclotron frequency, because of the circular motion of the charged object. So so again, we know that omega must have units of radians per second, and you know the unit of the radian must appear or disappear as needed. One can go back to this equation, and one can actually solve for the radius. And so the radius of that trajectory then is going to be then mv over qb. And so one can solve for the radius of the motion. If we have omega, then we can actually solve for the frequency, because we know the frequency is omega over 2 pi. We can also solve for the period. We know that the period is 1 over the frequency. And so all kinds of goodies come out of this analysis, right? And again, the units here are going to be hertz. The units here will be seconds. Okay, so let's end that installment right now, and I will continue on with some other really fun examples of using the magnetic force on charged particles. Okay, all right, take care.